At the software level, we're designing an instruction set that has all of these arithmetic operations. In a couple of weeks, we'll talk about what happens. Maybe we can use software to fake any missing instructions in the hardware. And in fact, we'll show you how that could work in our machine. So it's not clear that every machine needs to implement every possible instruction, but we have to implement enough instructions that we can fake the instructions in software for any operations that we choose not to implement in hardware. So here's a set of operations: the compare instructions, the Boolean instructions, the shift instructions, and the arithmetic instructions. And the way this works is that we're going to encode the two register operands, where we want to read the values from. Okay, and so if we want to read from R2 and R3, you can see that this is the format of this instruction here is sorry, if we want to read from R1 and R2. So the order of the operands here in our symbolic representation of a single instruction is RA and RB and RC. So R1 and R2 are the two registers we want to read. And you can see we've encoded 00001 as the encoding for the register 1 in the RA field, and the register, the numeric binary value for 2 in the RB field. So that's specified. Please read register 0 for the A operand, or register 1 for the A operand, and register 2 for the B operand. And this is the operation I want you to perform. I've encoded add using this particular combination of the 6 bits, and put the answer back into register 3. Right, so suppose I wanted to do the instruction. I'm just going to write up something else here. So suppose I wanted to say multiply R3 times R5 and put the answer into R17. Any conceptual problems with how you could take this sort of symbolic representation of an instruction I wanted to execute and encode it using those bits? Right? You know what to do with these three values, right? These go into the RA, RB, and RC fields. So you need to turn each of these register numbers, 3, 5, and 17, into 5-bit binary values and just write those little 5-bit strings in the right place in the instruction. What else do you need to know to complete the encoding? I would need to know what the 6-bit opcode was for multiplication. Alrighty, so now we have, the next 40%, 45% of the instruction set, which is the also ALU operations. What's the difference between the instructions on this page and the instructions on the previous page? Well, the answer is that the difference is that, first of all, that different opcodes. So this is another set of opcodes, another set of whatever it is, 16 opcodes. This uses the second format of instruction. So there's a bit here in our opcode encoding that tells us we want to use a different format of the instruction, which means the second operand is actually encoded as a 16-bit constant in the instruction itself. So instead of the second operand being from a register, is actually a 16-bit number that is part of the instruction. Now we need a 32-bit operand. What do I need to do to convert a 16-bit number into a 32-bit operand? I need to sign extend it. It actually doesn't involve any hardware, but you do have to make 16 copies of the high order bit of this numeric constant here, of this bit here, in order to convert a 16-bit representation of an integer into the equivalent 32-bit representation of the integer, which is actually what gets fed to your 32-bit data path. And we use the C here, to add constant, to sort of remind ourselves that it's somehow different from the operations on the previous page. So you say to yourself, well, do I really need that? Couldn't I put all the constants in memory and just sort of, I haven't shown you load and store yet, but I will in a second. Couldn't I just load them into a register and use them there? What's the advantage of encoding constants in the instruction? Does that actually bias anything? Will my program be shorter? Will it run quicker because I don't have a memory access to get that second operand? Is there some advantage to doing that? And now we get into the sort of technique that I was talking about before, the political people call it polling, we call it benchmarking, where what we do is we pick some programs whose performance we feel is representative of the type of programs people will be running our machine. In this case, this particular set of benchmarks, which was from Hennessy and Patterson, famous architecture textbook. The TeX word processor, SPICE is a circuit level, like JSON, circuit analysis program. GCC is the GNU C compiler. And what they did is they basically tried, they built a compiler that knew about these instructions with constants, and then they went off and said, well, how often do I use this feature? Is this like a feature I use all the time? And the answer is, it turns out almost all the comparisons that are in most C programs are comparisons to these small constants. Almost always when you say, well, you can see, 80% of the comparisons are actually against some small number, 3, 17, something that fits into a small integer value. Okay, over about half the arithmetic operations, one of the operands is a small number. We'll talk about loads and stores in a second. So you can see here that in fact, almost all the time, making a provision for arithmetic operands, for integer constants as one of the two arithmetic operands, is really quite useful. So this feature appears in almost every instruction set, the ability to encode constants as part of the instructions directly. Okay, so here we have our first little program. We're going to take the contents of R1, subtract 1 from it, and put it into R2, and then we're going to take R2 times R1, so if R1 contained n, so R2 now contains n minus 1, so we're going to take R2 times R1, so that's n times n minus 1, put the result in R2. So these are two separate 32-bit words that would live in memory that would encode the operation we would like to do. Now I'm going to add one more feature here just before we end the lecture. We have 3 or 4 more minutes, and I'm going to use them to talk about loading and storing information from memory. So we have a load operation and a store operation, and they both use the second format of instruction. So the two operands to the ALU will be the contents of a register and this 16-bit constant. Those are used with a plus operation. We're going to have the ALU do a plus for us. Those two values, these two 32-bit values, are added together to form the memory index, the memory address that we send to memory. We get back the value from memory, and that simply gets put into a register. So the load thing is computing an address by adding a register and a constant. So we have different ways of, depending on what that register value we choose and what constant value we choose, we have a way of computing the address of the location that we want. We can send that to the memory, a data value comes back, and we take that and we stick it into the RC register, whatever register we specify. And store does exactly the same address computation, but instead takes the value of the RC register and sends it to that memory location. So load and store are sort of symmetrically opposite. So now we have a way of moving information to and from our scratch pad. Everybody, so the arithmetic operations, with or without an integer constant, is the second operand, and then load and store. So this is what we call a load-store architecture, because the only way we can reference memory at all is either we can load a value from it or we can store a value into it, but there's no other instructions that reference memory. Okay, it reference memory as data. All we can do with memory is load and store. So the way we do our storage conventions is that when we have variables in our C program, here's x and y, we just allocate 32-bit words for them. So if we have a little program that has variables n, r, x, and y in it, what we do is allocate specific memory locations. And here you can see x was stuck in the memory location whose address was hex 1008. These are all hex numbers here. And so we use a load instruction to compute that address. We actually are adding 0, that's the contents of R31, to this constant. So this is really a constant memory address. And going out to memory, getting the contents of location 1008 hex and sticking it into R0, doing some multiplications, in this case by a small integer number, and storing the result back as the value of y. Okay, and sometimes instead of building in numeric constants, we use this sort of symbolic representation for memory addresses. We'll talk more about storage conventions next time. Now, you can say, well, Computing memory addresses, there must be 1,000 ways of doing that. I mean, and in fact, this is a set of the memory address operations that are available on an old style machine from the 80s. They got quite complicated. They were all set to, in a single instruction, be able to index into Fortran arrays of integers or reals or doubles or things like that. And you sort of go, well, these are all very complicated. The beta can do the ones, the instruction set that we just designed can do one of these three. It actually does displacement all the time. But if you specify R31, that's like absolute. And if you specify a constant of 0, that's like indirect here. So this is what we can do. Do we actually need all of this? I know. What does the audience say? And so we do our benchmarking, and we can see all these complicated modes, although they seem very appealing to us, turn out to be not very useful when it comes to, most programs don't use them very often. So instead of putting in a lot of extra hardware, we choose to leave it out and say we might have to fake it with a couple of instructions in a row, but we do it so rarely that the program will hardly be any bigger or take any longer to execute. Okay, so I'm going to stop there.